Hello. So I'll be discussing your digital image processing image enhancement second part, that is the spatial filtering. So we'll be doing it in two lectures. So this is the first lecture. So going ahead, we have already discussed the image enhancement using point processing and your histogram equalization. So here we'll look into the neighborhood operation, what spatial filtering is, what are the different smoothing operations, what happens at the edges, correlation and convolution. First, coming to the neighborhood operations, here what we deal is whenever we do some operation, we do it in a particular pixel. This is the center pixel, and then we can define the size of the matrix. So it may be a 3 cross 3 window, 5 cross 5 window, 7 cross 7 window, and whatever the computation is done is applied only on the center pixel. So neighborhood operations simply operate on a larger neighborhood of pixel nearby, 3 cross 3, 5 cross 5, 7 cross 7, or maybe higher also. So that is similar to the brush sizes that you are having in paint and other things. So as the brush width increases, the number of pixel increases. So these neighborhoods mostly are rectangular, but you can make it circular also if you want. But in that case, you need more number of pixels. Now, any size of rectangle or any shape of filter are possible. Here you can make circular, triangular, or any other thing. But the most popular one is the is rectangular, and sometimes for present day apps and other things for image editing, they use circular also. But the width of the circle changes. Now, the simple neighborhood operations that are available, mean, max, median. So here what happens, if I have a 3 cross 3 value, then the center pixel is replaced by whatever is the, in this case, if there are 9 pixels, whatever is the minimum value of 9 pixels, that comes into the center. Similarly, in max, the maximum value of the 9 pixel come. And in median, what we do, we arrange the 9 values in ascending or descending order, and the center value means the fifth value will be the middle, will be coming in the middle. So this is very beneficial, and I'll be discussing the median filter in more details. Now coming to, these are simple neighborhood operations that you can do. And like for example, whenever we have this pixel and we have say original pixels a b c d up to I, and the filter pixel r s t to z, when we do this is called convolution kind of thing. We do each and every pixel position wise pixel based multiplication. So v is multiplied with e, then v is in the center, so v and e are multiplied, r and a are multiplied, s and b are multiplied, c and t are multiplied, and so on. So this above process is repeated as we move one by one to the pixel. After E, we go to the next pixel, next pixel. So this is for 3 cross 3 filter. Now, if it is a 5 cross 5 or 7 cross 7, this particular process T will change in the equation only. Next, coming to this spatial filtering, you can see here fxy is there. This you can put different weights here. So here, this is the Windows center is 0 0, and -1 -1 -1 0 -1 1. Similarly here 0 -1 0 0 0 1. So here this is the center one. So here and here in the x-axis, when you are moving, you are either doing a -1 or a +1, and here in the y-axis you are doing a -1 or +1. You can see here, and this is the operation that is done. So it is a double summation for the window. The window may be the window that we are discussing here. Any window, I'll be discussing those. Now the most simplest one is the averaging. So if you have 9 pixels and you do averaging of 9 values, so you can multiply 1 by 9 to all of them, or you can consider 1, and in the total you can multiply 1 by 9. So it is a simple averaging. If it is 5 cross 5, there will be 25 pixels, so it will be 1 by 25. Similarly for 7 cross 7, it will be 1 by 49, and so on. So you can see the operation, what is happening. This one, this operation for this one will be there, and the center pixel will be replaced by 98.33. So this is averaged value of all these pixels. So this 106 is replaced by 98. So let's go to program for this. So for here, I use h 1/9 of ones 3,3. So here I am using the im filter command and the average is there. We can add some noise and the noisy version can be averaged, and we can here we have taken the circuit image that is available. In one we have low intensity noise, in one we have high intensity noise, and this is followed by the averaging filter that we apply here. We also apply median filter. You can see the differences. So this is the image with low noise, image with average filtered image, and median filtered image, image with high noise, average filtered image, and median filter. So you can see the advantage of median filter. That median filter totally removes the noise in this case, and in this case we have speckle, but this particular picture is much better compared to the blotches of the average filter here. Okay. Next, we have the image smoothing example. So here we have, based on the size 3, 5, 9, 15, 35, we can increase the sizes. And based on that, you can see the bigger size, the more smoothing and more blurry it is becoming. Uh, you can see how the details are disappearing one by one for this particular image. So this is the image as we go ahead. So it's more becoming more and more blur. So if you want to see this, yeah. This is original image, median filter 3 plus 3, median filter 5 plus 5, median filter 9 cross 9, median filter 15 cross 15, and median filter 35 cross 35. Whereas for the average filter, this is the average filter 3 cross 3, 5 cross 5. You can see this is becoming more blur here. So whether it is this one, median filter based, or average filter based. So weighted smoothing filters are also there. Here what we are doing, here we are applying the more weight to the center pixel, and based on their distance from the center pixel, these are having distance of 1 and these are having distance of root 2. So the corner pixels are given less weightage, and two nearest pixels are given, diagonal pixels are given less weightage. The neighborhood of pixels with distance of 1 is giving more weightage, and the highest weightage is given to the center pixel. So when we do this type of operation here, it is same as earlier, only the formula of averaging is of 1/9 or equal weightage is replaced by different weighted kind of average here. So as it is 1 plus 2 plus 1, that is 4, then 2 plus 2 plus 4 plus 2. So here it is 8. So 4, 8 and 4. So it is 16. So you are doing 1/16 throughout. Okay, so this is a weighted average filter. So we can take the original image, you can smooth it, we can also threshold it. So if you want to see this, you can see here the snowflakes image, average threshold, median filter threshold. Similarly, if you apply multiple thresholds, this I think I have shown earlier. So similarly, you can do average filter versus median filter. This I have already shown you. So average image after median filter is much better compared to that with averaging filter, as it generates blotches. You have already seen that. This is the average filter and this is the median filter. So this is a much better condition. So there are some approaches with dealing with the edge pixels. We can omit the missing pixels. It can work on some filters. We can pad the image typically with either 0 pixels. We can replicate the border. We can truncate the border. We can allow pixels to wrap on the image. So there are different ways in doing that. So you can see what happens in the edges. So when it is 0 padding is done, you can get a boundary kind of thing. When it is wrapped, it becomes different. So this, when it is here, the black one is black, the white one is white, and here we have a boundary generated because of these edges. You can, I think you have seen this in case of this. When we generated this, Because of these edges, you can see here the edge is different. Whereas in case of median filter, you see the edges are, you can see what is happening to the edges here. You have a dark portion in the edge here, and for this one you are having a boundary coming for this particular averaging filter. Okay. Now coming to correlation and convolution. For filtering, what we have been doing so far is that we refer to correlation and convolution. These are two very important things, but before going to that, let me explain from the one dimension point of view. So if you see here, convolution is mainly having 4 steps: folding, shifting, multiplying, and adding. And if this is a black box where you have a signal xn coming and output yn going, so this is the equation of xn. Here, xn is a combination of different unit impulses, that is del n minus k multiplied by the coefficient value xk. And yn is output, and this is the transfer function here. So this can be written in this format, where h and k is the impulse response of this particular thing. When input is del, whatever is the response, when xn is equal to del n, then yn is equal to hn. So that is your impulse response. So if we know the impulse response, we can do. So mainly it is having the steps of folding, shifting, multiplying, and adding. I'll be discussing with an example. So this is the in general convolution equation. So this convolution summation we are having here. So this is the step for del n, output is hn. Del n minus k is hn minus k. Alpha into del n minus k is alpha into hn minus k. So xk into del n minus k is equal to xk into hn minus k. And summation of xk del n minus k is equal to xk hn minus k. And based on that, we had yn coming from this one. So yn is equal to this. Okay. So this is the whole equation, and it is commutative. Whether we do convolution of hn with xn or xn with hn, it remains the same. So the convolution summation consists of folding, shifting, multiplying, and summing. So if this is the sequence, you can see the sequence. So 1, 2, 3, 1. This is from the Prokis book solve example. Hn is this. So folded impulse, I have folded this hn. So it has become 1, 2, 1 minus 1 has become minus 1, 1, 2, 1. Here is the center pixel is 0. So it's around 0 it is flipped. So this is placed here. We do the shifting and we start off from here. Next step, we get this. Next, you can see slowly they are overlapping 3 pixels. First one only 1 overlap, 2 overlap, 3 overlap, then all 4 are overlapping each other. And as we go ahead, this train goes ahead and we have a total output based on this particular set of calculations. Now coming to correlation, we are having 3 steps instead of 4. The folding is deducted because here we are correlating 2 signals. Right? This is very common in radar and sonar, where signals are transmitted and reflected back. And like for example, if the signal sent is xn, so xn as it will go, it will be returning with a delayed version. So xn minus d will come back. Alpha is the attenuation and wn is the white noise. So the cross correlation is rxy, giving this. So this formula is similar to that of convolution. Only difference is that here we are having plus and yn, and if you see the equations, only difference is that the sign is reversed because of this folding not existing there. So if we come back to this, for images, we just do the same correlation convolution but in 2 dimension. So instead of the time axis, we have the spatial axis. So to show you, I'll correlate the images. So this is the cameraman image, original image, convolved image, convolved image. When we are using convolution based on the conv command is this, and when we are doing the simple averaging is this. Similarly, one is just filter based, one is using IM filter. Here we are using conv, and here we are using IM filter. So you can use convolution, you can use IM filter. When you use IM filter, the size is 258 into 258 because of the 3 cross 3 image being generated, and here it is 256 cross 256. You can see here this is 258 because here we are using uh, your IM convolution, and here we are using your IM filter. So there is the same size remains, but you can see the boundary. What happens in this one? A black boundary comes in one, a gray boundary comes. Okay. Now the next image you can see what happens for correlation. You original and less noisy version, original and more noisy version, median filtered, original median filtered, noisy median filtered. So we are doing the correlation of the two set of images. Okay. This is 2D correlation, convolved 2D correlation, image filter based 2D correlation. So in this lecture, we have looked into the neighborhood operation, filtering process, smoothing filters, how to deal with the problem at for image edges while using this filtering correlation convention. Next time we'll look into the sharpening filters. Okay. So thank you for now. I am pausing.